And I've got a, okay, I've got a hard stop at 3:30, but then if we want to, we can pick up at probably about 4.
Well, I think,
If
if we
there's,
can, if
yeah,
we can like box it into an hour, I think like I don't know what were you saying was
sure.
next. We did apply. Do you think reduce, or what do you think is?
Reduce is pretty simple. It's almost so simple that now you've seen um, apply, uh, it's like reduce is going to be super trivial. I could describe it quickly.
Well, and also like you can read go over concepts. People who watch this, there's nothing wrong with a little
Hmm.
reinforcement. And
Sure.
if we only have an hour, maybe reduces the way to
Yeah,
go.
I was going to suggest we try something like transpose, but that's a lot more complicated. There's several different transpose algorithms, um, and in fact, sometimes I use build to do the
Oh
transpose.
yeah. Oh, interesting. Um, so well,
So
but also
yeah,
there's a logical order potentially like apply reduce or apply transpose. Do you think?
uh, I think the lower level kernels are good to start with. Things like apply, reduce, transpose, select. Higher order ones, like the bigger ones, like assign. In terms of code size, right? Assign is huge.
Mhm.
Um, matrix multiply is huge. Uh, Algorithms for element wise, UIs add, UIs multiply. Those are a lot more complex. Transpose is fairly complex, actually. Um, the What else? Chroniker should be a fairly straightforward algorithm, but I've got a really slow implementation of it. My GRB Chroniker isn't very slow. It's not a high performance Chroniker product. I don't think anybody uses it, so I didn't put a lot of effort into it. It just works. But at some point, I need a faster Chronicle product.
Yeah. Well, and
Okay.
I've used it to build power law,
Oh yeah,
graphs.
it's
Yeah.
really useful for building big graphs for testing and such. But then when you're doing that, you don't care so much about performance. You just want it to work reasonably, not And it is parallel. Uh, yeah, it is parallel, but it is not at all very efficient.
Right, but it's
So
the traversal that matters, right? So
yeah.
yeah.
So yeah, we could do reduce. That's interesting, actually. It's got some interesting issues in it. Okay, so GRB matrix reduce. Well, this is GRB matrix reduce then to vector or scalar. All right. The GRB reduce to vector is actually very interesting problem, and you'll see how I do it. I think it's really cool the way I do it. I basically I cheat. It's actually a matrix vector multiply under the hood. I use the entire machinery for matrix vector multiply to do reduce to vector. And I do just a simple translation to that problem. And it always works, right? It's not like I'm missing anything. It's perfect translation. Okay. So this is reduced to vector or scalar. And reduced to a C scalar is painful because I have I don't know, 1,000. I have a bunch of C types to handle. Okay. Uh, but the very first thing I do with that is I let's see, yeah, um, is that I keep track of uh, I don't wrap the thing yet in a GRB scalar yet, but you pass in the C scalar as a pointer to that type. And the thing I do is I call one method with that pointer, but I pass in the corresponding GRB type that it is. So I know what type it is. So then I have one method called reduce to scalar. And the same thing is true with reduce to UDT. With reduce to a user-defined scalar, the only way that can happen is if you're reducing with a monoid that produces that exact type. There's no typecasting. So you must pass to me the type, the void star you pass to me must match the type of the monoid, which also then must match the type of the matrix too. Because the monoid only has one type it can work in, and there's no typecasting between user-defined types. So then I just know, oh, well, that must be the type you're passing me in. And there's no way to check that. You just give me a void star. I don't know what it is. It has to be. I can't verify it. But it must be that, otherwise you get a seg fault. Okay. So there's a reduce to scalar method is really important. And then it's one method to just pass in a void, and it gives I give it its type now that I've harvested. So I collapse all these 13, 14 different methods into one method, reduce to scalar. Or I have a reduce to vector, which is must essentially has to be done with a monoid. You got to give me a monoid. This is an abomination right here. GRB matrix reduced to binary op should not be in the spec. It's evil.
I remember. Yeah,
it is evil. It says, Tim, you don't need the identity value. Just reduce it. Reduce every vector. Just apply the the element pairwise. Well, yeah, that's possible. But if that's possible, it's also possible, just as possible, to say to matrix multiply, you don't need a monoid there. Just make the monoid, just say it's an operator. You don't need, Tim, you don't need the identity value. And that would be a true statement. GraphBLAS never needs the identity value, mathematically speaking. Now, it's computationally super useful, and I need it computationally. But mathematically speaking, you never, but once in the whole GraphBLAS spec, you do not need to ever know the identity value of the monoid, but for one place. And that place is very obscure. It's when you're doing right here, the reduce to scalar, not to vector, reduce to a C scalar, not a GRB scalar, but a C scalar. When you reduce a matrix or vector to a C scalar, what if the matrix is empty? Now we're talking about a niche corner case. The matrix or the vector has no entries in it. Well, then the answer is the identity value of the monoid. That's it. In the entire spec, that's the one place that's actually required, mathematically speaking, in the spec. Logically speaking, maybe I should say, in the spec.
and we're talking about taking that out anyway.
And I'd like that to go away anyway, right?
Yeah.
So this kind of this thing says, well, let's take that to the extreme. When you reduce to a GRB vector, then you can pass in, you can have if the row has nothing in it, just there's the vector is sparse, so you have nothing there. Sure, okay. But my implementation, so I'll say one thing about this anathema here. The way I do it, the way I implement it, I say, oh, you gave me a binary op. I really want a monoid. Okay, let me try to find its monoid. So I have a function called binop to monoid. I take your operator and I'll say, nice operator, do I know the corresponding monoid for that operator? And I'll use that. And I'll say, you didn't give me the identity value. I have it now. And I'll then call reduce to vector with that monoid. And if I can't find the monoid, I throw my hands up. Like if you have a user-defined operator, I don't know what monoid it corresponds to. I say, sorry, go away. You can't do this. I refuse. And this is unfortunate. I really never wanted to ever say, I didn't implement this. It's part of the spec. I refuse to implement it. Nobody cares. Nobody's asked me for it. Nobody wants it. Nobody needs it.
Yeah, I agree. Yeah.
But it's sort of like nagging. I'm not 100% complete. It is possible for SuiteSparse GraphBLAS. It's a complete implementation of the GraphBLAS spec, and it's got all this extras GXP stuff as well. Oh, output 1.
Well, I'll bring it up in the meeting tomorrow that we should get rid of it.
And so I'll explain when I look at reduce to scalar and reduce to vector. When I go to reduce to vector, you'll see why this is so important. In fact, maybe I should do reduce to vector first, because it's actually in some sense, a very simple algorithm. Okay, so let me do that first, actually. GRB reduce to vector, before I do reduce to scalar. This is a very interesting algorithm. I have two ways of calling it then. You can reduce a matrix to a vector via a monoid or binary op, but in fact, it's just a monoid. Okay, why do I insist on a monoid? I'll show you, because it's so elegant to implement it this way. And it's so natural. Okay. GRB reduce, oh no, sorry, it's GB reduced to vector. Okay. This is so powerful and so simple. It takes 218 lines to express it. And that's the entire algorithm. We're done. It's that simple and that powerful. How do I do this? I convert it into a matrix vector multiply problem and solve. Look, I've got a semi-ring. Okay, I'm going to build me a semi-ring to solve your problem. So here's what I do. I first have to do the same thing everything does. You saw this for apply. I have to make sure everything's fine, right? You have a faulty matrix, a null, or whatever. You know, you didn't give me a good monoid. I return an error message, error result, and I do all my checks, debug checks. I get the descriptor as you saw before, because you can ask for, these are all just, you can complement the mask, you can do replace, see, and you can say transpose. And see, here's the thing, everything you want to do with reduce to vector, GRB reduced to vector, it's got a mask, it's got mask complement, it's got potentially the transpose. It's a complicated beast with just 200 lines of code, including the error check, because it's actually the same as a matrix vector multiply, which is itself a rich, powerful algorithm. Why implement all of that algorithm for reduce to vector, when I'm already doing all that work for matrix vector multiply? In other words, it's just a matrix vector multiply. So let's have 15,000 lines of code to implement matrix multiply. Let's just use that to do reduce to vector. And then I get all this richness of different algorithms and different optimizations and parallelizations, and it's a complex algorithm. So let's just let it all work, and it works well, works fast. Why replicate that for a special case when it just works elegantly and does all the right performance as well, which is very important, and it does all the math? So what I do, all the error check, make sure the dimensions are okay. Return if quick mask. That's a quick return that says, if the mask is not present and complemented, then just kick out. You have nothing to do. The answer is empty. You get the empty matrix, or you don't change the input matrix or something, depending on the replace. Return if quick mask is there in a lot of places. Okay, so here's what I do to take a matrix, and maybe I should do this. Do I need to do this? I don't think I need to do it on paper. I'll just explain it. So what I do, reduce a matrix to a vector. The first thing I'm going to create a like mathematically say sum the rows of a matrix to a vector. That's just A times the ones vector. So I'll build me a ones vector of all ones. And you might argue, and gee, that's expensive. Well, no, it's actually order 1 time to do that, because it's a vector that's dense and ISO valued. It's constant time for me to produce and to represent. Okay, so I create me a vector called B. The user doesn't see this on the outside, but it takes 200 bytes, 300 bytes to create, even if even if the matrix is hypersparse. It's 100 billion by 100 billion matrix. I create myself a vector of the right dimensions, okay? And the dimensions depend on whether you're transposing the thing or not. You can reduce a matrix to a vector, but first transposing it, which means you want to sum up across down the columns instead of down the rows. sum with the monoid. So I just simply created a new, just a temporary matrix that's ISO valued. Okay. And the type of which is matches the monoid. Okay. It doesn't really much matter what the type is, but why not? I just picked that. The type of the monoid. The Z type is the Z type of the monoid here that you've given me. Where is it? Z type comes from the monoid. So I build a vector whose type matches the monoid you want to use. Okay, just for convenience. Then a semmering has a monoid and it needs a multiplicative operator. So I want to do A times B and I give it the first operator. Because all I want to do is put in the multiply operator just needs to return the A matrix. B is just a placeholder that says do it for every row. Okay. So matrix times a dense vector. I have a kernel for that. And not only that, it's an ISO value vector, and the first operator doesn't even depend on B. I just know that's always there.
It just sort of
Okay,
fills
so
in for the math.
it fills in the math, and I have a kernel that exploits just this condition. So why write this kernel twice? So this
Yeah.
is reusing this kernel. So it's the first operator which gives you the value of A. Now,
So just to be clear for anyone who's watching, the second B is a dense ISO vector, so it's very small.
Yeah, in the memory, it's constant bytes.
And because you're never even accessing the ISO value, you don't even touch it.
Well, I set it all to 0 bits.
Right, but
just so it's defined, but I don't actually have to do that because I never read it.
But the first operator doesn't even look at it. Yeah.
Exactly. But it's just a placeholder. I don't even need to, I would not even need to do that line, but I do it just to make it a little bit more sane if I actually wanted ever to print the thing in debug mode.
Yeah, got it.
Because otherwise I'll never actually look at the thing.
Yeah.
Okay.
So sorry to break your flow there. Yeah, go ahead.
Yeah. So then I say, oh, what is this Z type you're dealing with? If it's user defined, well, I've got an operator for that. GRB first, blah, blah, blah. Well, unless it's complex, it's GXB first. Okay, so that's the multiplicative operator. What if it's a user defined type? There is no first, right? No problem. That's easy. It's just a mem copy. I'll make me one. I make an operator. Okay. And I cheat because I give that you can't build this operator yourself, which is kind of unfortunate. It'd be nice to say, here's a user defined type. I'd like the GRB first for that type. You can actually create such an operator yourself and have a function pointer that does that. It's Z equals X is the operator. But I have an opcode for this. So I create a new operator that if it's not user defined, it's got its own operator code called first. Okay. So I'm using a built-in opcode for a user-defined type, but I know how to handle this in my kernels just for this reason. Okay. So now, so I can support reduce to vector with user-defined types as well. So I can handle this operator in my matrix multiplies. I know how to do first of a user-defined type. Because it's just a copy. It's easy. You know what it is. It's copy those bytes over, right? If it's 12 bytes, copy the 12 bytes. If it's 20 bytes, copy the 20 bytes. And why not? Okay. It's just an assignment. And I have the type. In the JIT, it's just an equal sign. It's easy. Okay. So this cannot fail, by the way, because this particular doesn't do any memory allocation. This doesn't do any memory allocation either because I actually create the thing, I cheat, and I create the whole thing in static memory space on the stack anyway. So this can't even fail for memory. I don't even have to do a malloc to get this to work. So this is super fast, super cheap setup. Then I create a new semmering using all the all the architecture I have to create a new submarine. This could technically fail because you malloc 100, 200, 400 bytes or whatever. Technically, it could fail. So fine, it can fail. Okay. And that's it. And there's the end of the algorithm. Full stop. What is that? This is GBMXM. Okay. Let me go to MXM. Let's see. Oh, by the way, I'm very particular. I'm very persnickety about my uses of my formatting of my code. I want to show you what I just did here. By the way, this is really important to me. Whenever I'm so over the top persnickety about my code, when I call a function in my code, it's always function name space left paren, full stop. Why do I care about that? Because if I don't know in my code, where do I call a certain function, I can grep for that pattern. And that's all that will be. There are no places where I'll say GBMXM space, or just no space. Okay. So I call this thing in 3 places. This GBMXM is the entire machinery for example, GRB MXV. Like this is GRB MXV over here. And GRB MXV does the same thing. It gets the descriptor, it gets the mask, checks the input, and calls this workhorse kernel, which does the entire matrix multiply. And it's a matrix multiply because, in fact, inside GraphBLAS, there are no GRB vectors. They're all matrices anyway. But this is just GBMXM. And so everything I've done to optimize GBMXM is just used right here. And it's using almost all of the features of GRBMX, of the call that GBMXV uses. It's got the output matrix, which is actually just a vector. It's got the replace descriptor. It's got the mask. It's got the accumulator. It's got the subring. It's got the matrix. It's got the transpose descriptor. It has this cheap vector, which is so cheap to construct, I don't actually have to free it when that's done. Free all just frees the subring, I think. Yeah, I free the, oh, well, I do free the vector just in the vector v just in case. I don't think I have to free it because I think it's all statically created, but I do it anyway just to make sure I don't miss anything. And I have to actually free the subring because I did do a malloc for that, I think. Oh, because of the name, I have to malloc the string for the name, and the name of the thing has a very simple name in it. That's it. That's reduced to vector. So why is this powerful? Well, I don't have to write a reduced to vector, first of all, and it's a lot of work to write a code like reduced to vector. And everything I would do for reduced to vector is everything I would do for matrix vector multiply anyway. So I have that in there twice. And now think about what it takes, the level of effort then it creates to write a matrix vector multiply. This is at the same level of difficulty. Now think computationally, writing an algorithm to do these two things, reduce to vector on one hand, matrix vector multiply on the other hand. They're just as hard, just as rich in terms of computational optimizations and parallelism and all that thing. And if this needs the monoid with the identity value to make it go fast, okay, on the, say, the GPU, for instance, well, it's handy to know the identity value because then all little threads can, if they get nothing, they can just put an identity value there. They can very quickly, you can do parallelism if you have the monoid and the identity. It's really super computationally powerful to have that extra rich mathematical structure. And I don't have to write the same algorithm twice, and it wouldn't be the same algorithm anyway. Just a second. Oh, can we said 3:30? Yeah, I've got a meeting going on. Okay. Yeah, all right. Okay, sorry about that. That's my 3:30 meeting. Okay, so let's see. So that's reduced to vector. It's just an MXV, and it's that simple. Full stop. It's that simple or that complex, depending on how you look at it. This is why my insistence on G. If you give me the monoid for matrix multiply because you know it's a powerful tool to make a powerful parallel algorithm. But the spec says no, Tim. Just do a crummy reduced to vector that is slower because you don't have the mathematical power of the monoid, the computational power of knowing what the identity value is of an operator. Just do what you can. Just get it to work. It's doable. That could work, but it'd be slower. So why? Why should I do such a thing when nobody needs it? I can't think of a single example of anybody ever needing reduced to vector that just uses a plain old binary op. It's just not needed. That thing, if it was existed, would be slower, and it's hard to write. So it's mathematically nonsense to say to give it to me for the matrix multiply and not for reduced to vector when mathematically they're so similar and computationally so similar, and then refuse to give it to me for reduced to vector. Give me the stinking identity value. Just give me a stinking monoid. So sorry, I get rather intense about this, but I think it's just ridiculous. It's one part of the spec, which I think it's probably the most insane part of the spec, honestly. That I mean, I fought with the committee about this. I was really passionate about it. Explained all this to the committee, and they just insisted because it just was. They thought, well, gee, you can do it, Tim.
Well, I will quote you on that tomorrow.
Yeah. But I mean, gee, if I can do it, then just take it out of the semi-ring too while you're at it. Just delete the whole monoid. What do you need a monoid for, Tim? You don't need a monoid, and you'd be right. Just as right as you don't need the monoid for a reduced to vector. Same logic applies. So do it. Go ahead, do it all. I'll just take out the monoid, take out the independent for all of GraphBLAS. Well, that would be ridiculous, right? Because we need it. It makes things faster in parallel and all that jazz. Reduced to vector is an important algorithm. It's not like chronic product that is rarely used. It's interesting only kind of mathematically, and it just works. And yeah, I do need to write a faster one, but it's not a heavily used algorithm. No, reduced to vector is super important. Many algorithms. It's got to be fast. So I said, fine. If it's slow, I'm not going to implement it. If I don't know the monoid that you're wanting me to use, I just flat out refuse. And so this method, GB binop to monoid, where is this? It's just a big truth. It's just a big switch case. I think. Yeah, it's just like, oh, you gave me a max operator. Oh, you mean that monoid, right? So I pass in an operator. I find out its code, opcode internally. I say, oh, you gave me the min. You gave me GRB min uint8. Oh, yes, you mean GRB min monoid uint8. So I convert the binary op, into its corresponding monoid. And so you can do min, you can do max, you can do times, plus, any little Boolean bitwise, and that's it. Full stop. And if you give me a different thing, give me a user-defined operator, you give me divide. But I mean, what would it actually mean to reduce a vector a matrix to a vector where every row is the reduction when you're using an operator like divide? Think about that. You're asking me to do it in order or something like that? It's not commutative, it's not associative. I guess the spec, I think the spec requires that the operator be commutative and associative. I think the spec does say that. Great. That's just this step away from the monoid. Just give me the stinking identity value. Oh, yeah. Okay. So sorry, I'll get off my bandwagon, but reduce the vector. Mathematically, and computationally, it's powerful and fast to implement this as a matrix vector multiply with an iso-valued vector B with the first, in other words, I create a semmering that's the first with the first multiplicative operator and with the monoid you gave me, which could be user defined. And then I'll just create the right thing. I'll do the right thing with that semmering, and that's it. Okay, so that is reduced to vector. It's that simple. Okay, reduce to scalar then. And I do have a GRB, where is it? It's probably down here. Oh, I have a thing called, okay, this is just a wrapper. I have a GB scalar reduce. I have two reduced to scalars, actually. I have a GB scalar reduce because this was new. I would have just had this, but the spec first required me to write this first function. So scalar reduce, I basically, since I already had a reduction to a C scalar written for the spec, when I did reduce to a GRB scalar, I just map it over to the reduction to the C scalar, which there's the C value right there. There's the C pointer within my data type. Okay. And if I just make sure that this input scalar I'm creating actually has an entry on input, and let's see. How do I do this? No, it could be empty on input, so which means it's not defined, which is fine. Yeah, anyway, it works. It's very simple. And then on the return, when I get the scalar back, I make sure the result is either a full or sparse scalar, not bitmap, I guess. So reduced to scalar is the big workhorse to a C scalar, GB reduced to scalar. And that is this algorithm. And it's not that long. So now I have a C scalar I'm operating onto. Okay. I do all the typical checks, the typical waits, like, hey, the matrix isn't done yet. So this is an interesting wait condition. I wait if the matrix has pending operations. If the matrix is out of order, jumbled, I don't care. I'm reducing every scalar in the matrix to every entry in the matrix to a single scalar. The order of those entries doesn't matter. And if there's zombies, I'll handle that internally in the algorithm. So I don't kill the zombies first. I can reduce a matrix to a scalar. I'll just skip over the zombies. So that's the waiting. So I now have the matrix. I get the contents, the statistics information about and I set up my C scalar now for a temporary result. And I initialize it to the identity value just in case I don't know what it is. And then I reduce it into this scalar. Okay. And I can do this with the CUDA kernel. And if that doesn't available, I onto the JIT kernel or the factor kernel next for the CPU, and then the JIT kernel, the same process, and then the generic kernel. The CUDA kernel is kind of interesting. I check to see, hey, am I going to do this on the GPU? Great, let's call the GPU and reduce the thing. The output of the CUDA may actually refuse to reduce it all the way down to a single scalar. I might, in this case, return one of two things: a the scalar, in which I'm already done, or it may reduce it to a vector. That vector is of length. That's the V that you see there. that vector is of length equal to the number of thread blocks of the GPU. Because I've determined I do that if I have a monoid or a data type that I don't know how to, for all the thread blocks to cooperate atomically to reduce the thing to a scalar. A user defined monoid, for example. Some would work with the CUDA, some don't. Depends on the size of the number of bytes. And so if I do return a vector, I just keep going recursively. So now I've got the vector to reduce to a scalar. And the vectors now is equal to the number of thread blocks of my GPU that I use to launch the GPU, which is going to be 1,000, 10,000, whatever. I'll probably just end up doing it on the CPU. Just call myself, this is a recursive algorithm here. GPU reduced to scalar just says, fine, just keep going until you're done. It just could do multiple levels if it has to. So that's a very elegant approach to the CUDA problem of not really having good algorithms to reduce to all the thread blocks to cooperate to reduce to a single scalar. That could be hard depending on the monoid or the data type. I can't do it. So fine, every thread block reduces its own scalar, and I'll reduce it later. And this is how I do it. So then I may switch over to the CPU at that point. Okay, so CUDA has decided we're not going to do it. So now we do it on the GPU. Now I have several different cases. First of all, if there's nothing to reduce, like there's no entries at all, all the entries present are zombies, basically. So there's no zombies, there's no entries. If there's 10 zombies, 10 entries and they're all zombies, well, there's nothing to reduce. The work is done. Okay. The ISO case is really interesting. Okay. You can, in GraphBLAS, create a matrix that's 2 to the 60 by 2 to the 60. It's all equal to 1. And you could say, Tim, give me the sum of that. Well, that's actually easy to do. I can do that in log 2 to the 120 time. I can do that with 120 calls to your monoid, just with a logarithmic. It's like x plus x plus x, or is just x n times x. Or x times x times x is just x to the n. Okay, you could just change the operator just to compute the answer. Well, I don't necessarily can always do that. So reduce to scalar ISO uses the same kind of logic of let's compute power, let's compute x to the n with repeated multiplies, log 2 n of them in particular. So this is a case, GB reduce the scalar ISO, okay, where I have a worker function, which here is the case where I actually don't care about performance because I'm only going to call this operator log n times if you have n entries in your matrix. So if you have a matrix of 2 to the 60 by 2 to the 60, you have 2 to the 120 entries in your matrix, which is so big that if you tried to store them all, your laptop would become a black hole, right? It's an ISO-valued matrix in this case, so I don't need that much memory space, but it's big. But the log to that is 120. So we're only going to call this algorithm is going to recurse down at most 120 times. And so reduce worker, what it does is it says reduce, and even handle the case where n is bigger than int 64. I call it twice, once across the rows and then down the columns. Reduce to worker ISO. What does this do? There's the algorithm. It's just like, oh, I have n entries to reduce. If n is 1, you have the answer. If n is not 1, I reduce half of them to a scalar and then call the operator on itself, right? Right, it's just a logarithmic tree. And then if n is odd, I need to do it again on the input value, and that's it. So that's super elegant. And this is a function pointer, right? But I don't care. I'm not calling it that many times. So it's going to be very fast. Okay, so that's the ISO case. Very important special case. And it's important that it be I mean, super asymptotically fast, so it doesn't actually have to be parallel or anything. It's fast enough. Now, finally, the case where I can use the factory kernel. Factory kernel can be used if I'm not going to do any typecasting. So I've got the monoid. It's got to be fed in the values of the A matrix into the monoid. Well, there can't be any typecasting. If there's no typecasting, then I can potentially use a factory kernel. So if I go to the factory switch case, factory GB red factory, again, the factory kernels always look like this. They always start with this comment: define the worker for the switch factory. Here is the worker for the switch factory. Launch the switch factory. There's the switch factory. And here's the controls for that. So then here's the factory. It's a big switch case. If it's not Boolean, then I handle all these workers. And these call the pre-compiled kernels. These are not JIT kernels. These are not pre-JIT kernels. These are the factory kernels in the factory kernel folder. And there's not that many of them. There's min, max, plus, times, any, and then the Booleans. Okay. And so if we go to the factory kernel folder, cd dot factory kernels, okay, you look for red. Here they all are. Okay. These are very short. If we look for, say, the red plus, this is the reduce to scalar plus. This happens to be for the complex case, let's say float. Okay, this is reduce using plus with float for the factory worker. And I pull in one of two templates. And I'm going to do that for the JIT as well. So let's look at those templates. We're here now. Let's suppose you're using you've got an FP32 matrix, and you're doing plus FP32 on it because the type matches the monoid. So there's no typecasting. To reduce this thing to a temporary scalar, and it will then call this method. I've already determined how many tasks and threads to use. That's up here somewhere, the parallelism. So it's chosen once for everybody, including the JIT kernel, because it's pretty simple. Just how many entries you want to reduce, and decide on your number of tasks and threads based on that. And so, and a task for me is just a loop of a pragma for loop. And the number of threads is how many threads will I use to execute that loop. So I don't use OpenMP tasking directly. I did at one point, but not all OpenMP implementations, particularly Windows, do support tasks or OpenMP tasks. So I don't actually use OpenMP tasks, even though I call them that in my code. So let's look at these two templates. These templates now they're templatized, right? Like everything else is. And I have two of them. This is all the algorithms for both the JIT and the factory kernel. So let's look at both of them. The first one's a little more complicated, and thus, I think, interesting. Okay, it's a panel reduction. The way a panel reduction, and the panel reduction, though, requires two conditions to hold. I use it unless I have zombies. Unless it's a little awkward with this algorithm to leave things out. How would I leave things out? Well, if it's bitmap, you can only reduce the things that are there. If I have zombies, you can only reduce the things that are there, and you can't reduce the zombies. Everybody knows that, right? Zombies aren't reducible. So here, if at runtime I just check to say, oh, do I have zombies, or is the input matrix bitmap? Well, therefore I can use a different algorithm that is simpler and thus slower. Otherwise, I'll reduce to panels. And here what I'm doing is I have a special case, even for a single thread, this method is faster. If you have a bunch of matrices, you want to add them up, it's actually slow to go plus equals, plus equals, plus equals one at a time into a single scalar. It's actually a bad idea. Even with a single thread, it's better to do it this way. I have an array of size, whatever the panel is, which is by default, if it's not defined, 16 entries. Okay, the JIT kernel, depending on the operator, or the factory kernel, depending on the operator, like here, I decided that for float, reduction with plus, the panel size should be 64. And that seems to work well in performance. Otherwise, if I don't define it, it's 16. So it's even reduced to scalar with single thread. I'll use this panel. I'll reduce it to an array of size 16 first. Okay. So the first thing I do is grab the first panel, the first 16 entries of the matrix. And now I'm going to do is a double iteration. I'll do this in parallel as well. Okay. So I'll just iterate over in chunks, panel by panel, 16 by 16, or in this case, for float sum, it's chunks of 64. Okay. And within that panel, it's a reduction into the panel, not into a scalar. Now, why is that useful? Well, that's easier to vectorize. I have 64 entries into a panel. I go to the next 64 entries, I reduce them all into a panel of, say, 64, or by default, 16. This inner loop here, well, this is the last partial panel, but this inner loop here, sorry, here, the whole panel, that is easy for the compiler to vectorize for many operators. Like this is literally a panel of K. This macro is whatever it takes for this data type, for this monoid, to do this mathematical operation where plus is the monoid. Panel of K plus equals the entry from the matrix. Okay. There's another reason why the panel is really nice, because then, well, this is not very nice actually. If the monoid is terminal, okay, what it means, it can short circuit, like Boolean or, Boolean and, integer times is terminal, because if you reach a 0 integer, the result will always be integer 0. I'm sorry, if you just keep going, you can stop at 0. You've reached 0. You're not going to go any further. Floating point times, floating point plus, do not short circuit. You might think, oh, floating point times, if you reach a 0, you're done, right? Well, no. Technically, 0 times nan is not 0. 0 times nan, or 0 times infinity, is nan. So if you wanted to write a algorithm to do a reduction with times on float, then technically you could stop if you ever see a nan. Well, that's actually not usually worth exploiting, because how many nans are going to see in production? That's the right answer. So I have to get that nan as the right answer. I can't skip over and get the wrong nan result if you ever give me a nan. So I can't stop if I see a 0, because there might be a nan hiding down there that I didn't see if I stop early. So I can't stop at a 0. I have to stop only at a nan, but it's rare, so it's not worth exploiting. So I declared simply that the times float is non-terminal, a non-terminal monoid. But if it is terminal, well, how do I handle this? Is it only every so often, like every 256 panels, do I look at the whole panel and check to see if I found the terminal value? I check the terminal condition, and I just count how many terminal conditions. This is also easy to vectorize. I played with this, like even a break out of this is not so good. It's actually faster just to check to see if I found any this way. Okay, so that's the sequential algorithm. And then when I'm done, then I reduce the panel. And if you only have, if a matrix is smaller than the panel, well, this is the entire reduction right here. Okay, the parallel case is very similar to this. Okay, the parallel case has to partition this, so here's my typical parallel loop. What time is it? 3:16. I have some number of threads and I iterate across my tasks. So I determine what the tasks are going to do. Okay. Each of the tasks is going to do a panel reduction. Okay. But and this code looks almost identical to the one up above. It's almost identical, with the following exception. If anybody finds the terminal condition, and what's happening here too, by the way, is every task, if I recall here, think every task. Yeah, see, every task has its own panel because it's just declared on the stack right there inside the parallel region. So this panel is local to this iteration. So every task has its own panel. Every task reduces its result using the panel to a final scalar, and then that scalar gets written into an array of size 1 per task. It's been allocated by the caller. Okay. And then when I'm done, I just sum up this sequentially. So that's the parallel case. But the terminal case is kind of interesting to handle. I still, each task still only checks every 256 panels. But now one of the tasks says, hey, we can stop, guys. Hey, everybody, we can stop. We're done. We found the result. Well, how do I do that? I don't want to do this like this needs to be a little bit relaxed. I don't just terminate. I mean, if you're constantly checking the terminal condition, that'll be slow. So how do I do this? Well, this task can finish. If this task detects that it found a terminal condition, it tells everybody else, look, guys, you can finish. I do this through an atomic operator. I set an atomic early exit flag atomically. And so if a task is already started, it won't get terminated unless it finds itself a terminal condition. It'll just keep going. But you see, I have 64, I typically allocate a lot of tasks. Like if you have 100 threads, or say 10 threads, I'll create 64 times that number of tasks. So I have 640 tasks. So they'll finish eventually pretty quick because they're small. And anytime a task starts, I check to see if some atomically, this could be a race condition, but it'll still give the right answer. But it's atomic. Like, did anybody else find this? That, hey, we're done now, guys. We can stop. If so, it just doesn't do any work because we already know what the final result is the terminal value of the monoid. Every monoid that's terminal has a terminal value, and we're going to get that answer at the end of the day. So one of the panels has the terminal monoid. One of these values in the work array of size 1 per task has the terminal value. This, because the monoid is terminal, this final reduction will find that and return that one terminal value if they all exit. So that's the algorithm with the panel, both the parallel case and the sequential case. Okay, and it's surprisingly complicated because, I mean, sequentially, literally, I could just write this algorithm full stop. Just change the iteration. K equals 0, K less the number of entries in the matrix. Done. It's 6 lines of code. It'd be that simple. But reduction is a little more subtle than apply. Apply, the code looked like that. The loop looked that simple, basically. Reduction is a little more delicate because of the terminal condition and because of this panel idea, which is important for vectorization. That's not an issue with apply because it's already vectorized. It always just goes apply, just there, vector, vector. But reductions are different. And the reduction like that is hard to vectorize. We're just applying it to a single scalar. How do you vectorize that? You don't. You do it in groups. You do it in the panels. So I use that to get better performance. And then it makes a big difference for like plus. Makes a huge difference for say built-in monoids. Use these a lot, like plus FP32, plus INT32, whatever. They're going to use that. Okay. The other algorithm, reduce, source reduce template, is reduce to scalar template. This is my first algorithm. This is the simpler algorithm. It's super simple. Okay. But it's a little more flexible because it can skip over zombies. It checks for zombies. Single thread algorithm is very simple. It says, Well, if the matrix has zombies and you're a zombie, skip you. If you're a bitmap matrix and the bit says you're not there, skip it. Otherwise, get the matrix, do the thing right there. There's no panel. And if you've reached the terminal condition, stop. And that's a single-threaded algorithm, as opposed to over here, which is much more complicated. Which, it's not too bad on the left, but on the right, it's very simple. And the parallel algorithm is almost just as simple, except for the terminal condition. I think, yeah, I still use the early exit check here. In fact, I don't even bother. I guess I always read it. I guess I could have left out this atomic early exit, and I could have put if mono is terminal, I could have put this around it, like that. I didn't even bother to do that. I probably should. But this is not as performance critical, this algorithm. Anyway, because the same kind of same kind of thing is happening here at the very end. When I wrap it up, it still has this let's see, what does this do? Yeah, every oh, if I found any entry, I guess I worry about the case where the result, yes, so I don't actually stick in the identity value. I just check to see if it's found or not, so I can skip over it. But I sum up the final work in a final scalar here. Yeah, the same thing is done over here. To say the results of the task in this this step here. This could be a typecast, I think. And then I sum it up. So that is, those are the two algorithms, both the sequential and parallel variants of them for reducing to scalar. They're fairly simple algorithms. Even the panel reduction is not that complex of an algorithm, but it does have some subtleties to it. And I don't always use this. This doesn't work if the matrix is bitmap, because now it gets a little bit awkward, right? If I have to skip over parts of the panel, I just decided not to do that, because I mean, reducing a bitmap matrix to, yeah, I guess, reducing a bitmap matrix to a scalar. Okay, it's not as fast as it could be because it's not vectorizable, and it just was simpler to skip that case and use this more flexible algorithm here on the right without the panel. So this algorithm over here on the right is one I wrote first, and then I realized in some cases it wasn't as fast as it should be, and so that's why I wrote this faster method, which it's more easily to vectorizable. Okay, so I'm almost done with reduce. Finally, let's see, reduce scalar, I'll call it. This is the, whoops, reduce to scalar. Okay, so we're back here. We've done either those one of two algorithms, either with the factory worker. If that failed, we call the JIT. The JIT uses the same two templates. If there is no JIT enabled, everything's mem copies and function pointers. And here I do actually have a generic case that doesn't have to do any typecasting. I can just do mem copies and with no moving data around with no typecasting. Okay, I don't use the panel if it's generic. I just use the simple method. If there is typecasting, I have to do the typecast here. I change this macro to do the typecasting. And it's going to be slower because it's again through a function pointer. Now comes the very last step. I have a scalar. It's called Z, because that's the type of it, is the Z type. I'm not done. Because oddly enough, in a very strange way, GRB, say, reduced to scalar, you can pass an accumulator, but you can't pass a mask. This accumulator is going to be used on a single scalar. Okay, but it is not the same as the accum mask phase because there's no mask. It's not the same as the accum mask phase of most GraphBLAS operations. The GRB reduced to scalar is an outlier. It uses a C scalar, which is evil for one, but let's ignore that for the moment. You can pass an accum, but you cannot pass a mask. It masks a single scalar, I guess. So what this means then is I have to have a special accum step entirely for that one scalar that's left. So I thought about how to do this. I could hoist this up. I got just a couple of minutes left. I could hoist this up and convert it into two matrices, and a mask passes null. I could call my accum mask process. That felt like overkill. And so I just hard coded it into this algorithm. I encoded, and I don't use, I just use function pointers all the way through, and function pointers for typecasting, function pointers for the function, the accumulator, and so forth. Just it's all function pointers and mem copies. It's always generic if there's an accum. So yeah, it could be slow. Well, yeah, but it's a scalar code. It's doing one, calling everything. It's just doing once. So and it's different. It behaves differently than there's like, how does it work? You always call the cumulative. There's no bypass the cumulative operator because it's a C scalar, which is always present. You see, that's different. When you have a cum and there's no entry present, it behaves differently. You don't call the accum operator. This is different. It's always present. The C scalar is always there. There's no such thing as a sparse C scalar. And so it's in some ways simpler, and it's different. So I just hard coded it directly. So anyway, so and to do that, I haven't shown you this yet, and I don't have time at this point. I'm running out of time. I have a thing called a cast factory. And what this does is I pass it two type codes, because you can't pass cast between user-defined types. And if they're both user-defined, it's just a mem copy. That's easy. So literally the cast function is just a mem copy. So I handle that. The user-defined types come here too. What the cast factory does, it returns a function pointer to one of like 13 squared functions. There's that many of them because it's just a table of functions that cast from int 8 to double, from double to int 16, from blah blah blah, from UDT to UDT. It's just a mem copy. From float to float, it's just a mem copy. This cast factory returns a function pointer, which then does the right thing. So that cast factory is handy because it allows me to write code like this that I can just, it's not going to be high performance, but only calling it once. So doesn't matter. I don't think I use the cast factory too often. I use it when I need generics. So you'll see it a lot. You see it a lot of places. Okay. But all these places, well, here, even the function name says this is the generic method. If you look internally to all these codes, these will always be places where I'm about to call the generic kernel. Most of them, except for this. Even if I JIT the thing, I'll use this code because I only need to do it once. So the performance doesn't matter. If you reduce a matrix of 1 billion entries down to a scalar, and I call one function pointer a few times, you'll never notice. So
All
Cast
right.
Factory appears in lots of places. Anyway, so yeah, it's 3:30, and I'll have a student waiting at the door for me shortly.
Sure.
Um,
Yeah. Don't want to keep waiting.
but
All
but
right. Well,
yeah, that's reduced to scalar and reduced to vector.
cool. Well, I'll send this around when it's done. And, if I have any other questions about that type stuff earlier, I'll let you know.
Yeah, sounds good.
All right. See you
All
later,
right,
Tim.
catch you later. Bye bye.